ahead and get started. So I wanted to just remind everybody what the Euler method was, because we're going to see it here in just a moment. So if we just use the definitions of velocity, so velocity is dx by dt, let's write it as dx by dt equals velocity. And dv by dt is equal to the acceleration, and we'll just assume that this is constant. So we can remember that we just take our finite difference formula, and so for the definition of the derivative, this will just be x at t plus some forward times tau minus x at t over tau is equal to v some time t. And so we solve this for the forward time and write that x at t plus tau is equal to x at t, the position of the former time, plus tau times v of t. Okay, so this would be a position equation, and then similarly, if we just do the same thing for the velocity, then we have v at t plus tau is equal to v at t plus tau times a. And that's the Euler. Now, what error are we actually making? In the truncation. So let's go back to our first derivative formula, or let's just look at the Taylor series for a function. So if we take f of x plus h, where that's just some small displacement, this is f at x plus h times f prime at x plus h squared over 2. And now I'm going to write this as f double prime of zeta. Okay? And I can truncate this formula. This is exact. For some value of zeta that's in the range x and x plus h. Okay, so that's an exact formula. We're still going to truncate it. So let's again solve for f prime. So we'll have f prime of x. Now this is f at x plus h minus f at x over h. And if I move this term that has the h squared to the other side and then divide by h, I'll have minus 1/2 h f double prime of zeta. Okay? And this is the piece that we're going to drop. We're gonna truncate this. Now, it's h squared here, but when I divide by this h, I'm going to take one of those h's out. So, in fact, this formula is actually order h. So, f prime of x is f of x plus h minus f of x over h plus something of order h. So, that's the actual error that we're making. Okay, is h to the first power. Now, this is called the forward first derivative. And let's see if we can do actually better than order h. So now let's write f of x minus h, well, let's first do that f of x plus h again. This is f of x plus h f prime plus h squared over 2 f double prime, and then let's see, let's truncate here, so this would be h cubed over 3 factorial f triple prime of zeta 1. Okay, and then let's do f of x minus h. So this is f of x minus h f prime of x plus h squared over 2 f double prime, and then minus h cubed over 3 factorial f triple prime of zeta 2. Okay, now, these terms here are not the same. This is exact for zeta 1 in the range x to x plus h, and for zeta 2 in the range x minus h up to x. Okay, they're different actually, because the intervals are different. And now we can go ahead and subtract these two. So let's take f of x plus h minus f of x minus h. So on the left-hand side, we'll have f of x plus h minus f of x minus h. So if I take this series and then subtract off this series, I'll cancel out my f's, and then I'll have plus twice, I'll have 2h f prime of x. I'll subtract off my squares, so these terms will cancel, and then I'll have plus 2 times h cubed over 3 factorial, and then we'll have f triple prime of zeta 1 minus f triple prime of zeta 2. Okay? So this is the actual error term. This is the error term. Okay? So now, let's solve for f prime. And this time when I do this, I'll have f prime of x is equal to f of x plus h minus f of x minus h over twice h. And then now I'll have, if I divide an h out here, I'll have something that's of order h squared. So this is called the centered first derivative. And the error here, the truncation error, is order h squared. Okay, so that's a much better truncation error. So for small h, this formula should give a much more accurate answer for the derivative than this formula. Yeah.
So higher order is more accurate?
Yes. So, if h is, we're assuming h is small, right? So if h is 0.1, h squared is 0.01, h cubed is, right?
So that makes sense, because for it to be the derivative, we are looking at very small, so we should be at less than 1.
Yeah.
Okay.
Yes.
Yeah.
Right. Okay. So that's how you calculate the order of the errors. So we can calculate it now for the second derivative. Since we've already written these down, let's go ahead and. So how about the second derivative formula? Centered. And we get that just by, adding these. So if I add these, I'll kill the first derivative terms and the third derivative terms. So there's actually an order here that's ordered fourth. Okay, so let's go ahead and add them. So here we'll have f of x plus h plus f of x minus h. This will be twice f of x here. I'll cancel out my first order terms. I'll get a second order term here, which is plus h squared. F double prime of x. I will cancel my third order term so that I'll get a fourth order term. So I will have something here like plus h to the fourth f4 of c1 plus f to the fourth of c2. And there's some other over 4 factorial here. Okay, so now when we solve for f double prime squared, or sorry, f double prime, we'll get f double prime is f at x plus h plus f at x minus h minus twice f at x divided by h squared. And then because this is an h to the fourth, when we divide by h squared, we'll again get something that's plus order h squared. This is, it's also order h squared. Okay. All right, are there any questions on that? Okay, so, all right, let's do a demo here of just calculating a trajectory using the Euler method. Everybody see the screen okay? I have some lights here. Cursor's on that screen, so it's not on this screen. There we go. Okay. Okay, so here's Octave, and let's do the simplest thing that's possible here. So remember again that we can work with vectors here. So let's suppose I have, the vector x for position, and I'll start this out at, 0, 0. Okay? So the x1 is the 0, it's the x position, and x2 is the y position. And let's give a velocity here of, let's give it 10, say, meters per second in the x direction, and then 40 meters per second in the y direction. Okay, so these are our initial conditions. And now let's just Euler step them. So we have, in order to Euler step them, we have to define a time step. So let tau equal 0.1, a tenth of a second. And we just want to integrate these things forward using the Euler method. So that means I update, all I do is I update x. This is equal to x plus tau times the velocity. Okay, so I've already updated it. That's my new position for a tenth of a second. And then I can update my position. Well, let's set the acceleration. So the acceleration say is 0 in x and minus 9.8 in y. So this will just be gravitational acceleration. So then I can update my velocity, and so the velocity is it's starting velocity plus tau times the acceleration. Okay, so you can see here at the bottom that my velocity is the same in the x direction, it's 10, and in the y direction I've slowed down a little bit because of the acceleration of gravity. And so we can just continue to integrate this. Now I'm going to update x again with my Euler step. And then I'll update v again, and then update x again, and then update v again. And you can see that the velocity here is just is slowing down in the y direction because of the acceleration of gravity. Okay, so all I did here was type in, three little lines. That's all there is to integrating forward with an Euler step. Okay, so let's look at a piece of code now. Okay, so this is, the other thing I wanted to point out, in your workspace over here on the left, you can see all of the variables that you have defined in the problem, and you can also see what kind they are. These are all floating point numbers. You can tell the dimension of their arrays. So A is a 1x2 array, tau is just a 1x1, it's just a number, and so on. And then you can also see the values here. So you have information about the variables at hand, especially if you're debugging or something, and you're stepping through the program. Okay, so here's this is the ball E program. So there's code for this in the book. I made some small changes to it just to solve the problem and whatnot, but you'll do this when you're working on the homework. So remember that, as you look at all of this code here, just remember that there's only 3 lines that are important. The rest of it's just, it's just all the infrastructure around those 3 lines. And this is just to set up variables and print statements and stuff like that. Okay, so, don't be afraid of the program, or just because it seems like there's a lot of lines. All right, so you can ignore a lot of this stuff. I don't even think I need this stuff anymore. I just did that because my old computer needed GNU plot. I would go with Qt. I think that's the better graphics package now, but this is old code. Okay, so we talked before about what you have to do for this problem, that when the ball crosses the line, when you calculate the trajectory, the ball's gonna come up and it's gonna land, and you're going to have, you know, you're gonna have something like this. You're gonna have, you know, you're gonna be calculating these points, of course, you're not gonna calculate the line. And when you get down to the end, you're gonna have to calculate this crossing point. And so you're gonna use the last 3 data points so that you can actually calculate that location. Okay, and you're gonna wanna calculate it in time and in position. So what do you do here in the code? Let me see if I can make this bigger. Okay, so in the code, I'm going to calculate the last 3 data points. So this is last point 1, 2, and 3. I've got a slot for X and a slot for Y, so you can just collect the last 3 data points there. And then I'm also going to save some space here for 3 time points that go with these last 3 data points.
So you just set them to 0 as like initial points?
Yeah, just to initialize them.
Okay.
Okay, and then, so here we go, we'll set the initial condition. So this is the BALL-E program. You want to enter the initial height in meters, and so that's going to be y1. So the initial position vector, now they call it r instead of x. They call it r1. So the initial position is 0 in x and height y1. And then you have to enter the speed and the direction and angle, and then what kind of I think he only does Euler, but you'll code up Euler-Kromer as well in your program. And then we just calculate the velocity here, right? This is just the cosine and the sine of the speed. So in the x and y components. And then now we set the final initial positions here, which is just r and v. So these are vectors. R is a vector and v is a vector. Now, I've added stuff here for drag. You're going to add drag to the program. So you'll have to add, you know, the drag coefficient, the area, the baseball, or whatever it is, the gravitational, the gravitational force was there beforehand, and then the mass of the projectile. And then you can also set a flag for if you want to calculate the air resistance or not. And so if we don't calculate the air resistance, we just set the density of the air to 0 for no air resistance. And then the density of air at the Earth's surface is 1.2 kilograms per cubic meter. So we either just turn the density on or off. And then, so all of the constants that are in the drag coefficient, or the drag here, are right here. Okay, and then we enter a time step. And then if you want, you can set the maximum steps to, you know, whatever, if you're afraid of going over. And then you start calculating. So all of this code here is, so this is, I'm setting x plot and y plot. These are arrays now for plotting the actual trajectory. Okay, so wherever, when we were stepping through the position, you know, you can peel off the x position and the y position here and then put them in arrays. This array is indexed by the loop index. So that will just collect the x and y positions for the trajectory. And then the current time is just the number of time steps minus 1 times tau. And then if you're calculating with no air, so if you're calculating with no air, this is the calculation. This is the Euler calculation. So we've got the x position just goes to, it's x is equal to the previous value of x plus the velocity times the time step. And if you have no air, the only acceleration that you have in the problem is the gravitational acceleration. Okay, and then if you do have air resistance, then you have to calculate that acceleration. And remember, we calculated this in class, but basically it's the norm of v times v. So this will always, when we calculate it, it will always oppose the forward motion. Okay. And then here's just the loop over either Euler or Euler-Kromer. And then down here, record the last 3 points for the interpolation. So what I do here, I mean, you can pull these off after because you're collecting X plot and Y plot. So you have these arrays that actually have the data points in them. Another way you can do this is I just keep updating them as I'm going. And so I'll put the latest position R in last point 3, and then I'm just filling these 3 up in a sort of cascading way. You don't have to do it that way, but okay. Anyhow, so here, this is the braking step. So if R2, which is the Y value of the projectile, if that's less than 0, then that means that the ball had to, it's below ground basically, right? So it already hit. And so you record the final last values, and then you break out of the loop. Okay, and then that's it. I mean, that's really it. The last X value that you collect is something that's going to be a little too large because you're already past it. The ball already passed the ground, the surface, and the Y value is too low. So Y is negative at this point. So if you take those last 3 points, then I can put them into just some other arrays here, and you can use the interpolation scheme that we talked about before, which is this 3-point interpolation to calculate those values. So let's go ahead and run this and see what happens. So let me I just cleared off all of the values over here. Okay, so let's start off with 1 meter in height, and we'll do 45 meters per second at a 45-degree angle, and then let's do just Euler here. And then we'll use air resistance, and then we'll use a time step of 1/10 of a second. Okay, so you can see, first of all, you can see the huge difference between whether or not you have air resistance or not. And also, you can see the last 3 data points here. The last data point here is off, it's below ground, and then so it's got too large of an X value, and you're actually looking for, let's see if I can zoom in here. Maybe that was too much. Okay, so I've marked it. So that's the actual point that you want, which is not, you can tell by the spacing that these 3 points are the last 3, and then this is the one that I calculated from the interpolation. So when you work the problem out in your problem set, you should plot this so that I can see that you calculated the correct point.
I have a question.
Yeah.
Maybe I missed it, but, was air resistance affecting the X velocity as well?
Yeah, well,
Okay, cause I didn't see it in there, so I just wasn't sure.
yeah, it'll slow it down.
Okay.
Well, it's in the V,
Oh, okay.
it's in the velocity. You calculate it's right here.
Oh, okay, yeah, cause the V includes both vectors. I think
Right.
I'm right as a Y.
Okay, are there other questions? Yes?
So the homework for this week doesn't mention the Cromer method, I don't know if that's next week's thing,
Well, I talked about it briefly, but we can,
well, then we do it.
Huh?
In the writing, it doesn't say, in the problem description, it doesn't mention
the Cromer
Cromer
method.
method at all.
Oh, well, that's fine.
Okay.
For this problem, it's not, Cromer method's not really critical. Okay. And then, so here at the end, you can see I've printed out. So the calculated time of flight is 5.5 seconds, right, which is a multiple of 0.1, because it's just the last data point where it went below ground. So the interpolated time of flight is 5.34, versus, sorry, 5.437. Okay.
Yeah, if we did a really small time step, then it might not, the time would end up being like too large and it wouldn't fit in the graphs. Like, wouldn't that be what the max time would probably be for?
I'm sorry, say that again.
I was just thinking that like, if you made the times at like 0.01, like what would happen?
You'll get the same plot, I mean, unless, if you make it too small, you'll hit my 1,000.
Yeah, that's what I was saying. I was like, that's probably why you wouldn't do it that small.
But, ideally, if you have a numerical method, you would try with different time steps and see, where you get better accuracy and that kind of thing. Okay.
I feel like this would be a good class to learn how to write a physics engine.
Yeah. I mean, gamers do that. Right?
Yeah.
But I hear they don't get paid, gamers don't get paid very well. People who program.
Yeah. As soon as you put a little bit of art in it somehow, just like, yeah.
Okay, so things to test with your code when you calculate the code. With no air resistance, you want to calculate the things that you can calculate analytically, like the time of flight and the maximum height and everything like that. So Y max, this is just the, remember from your freshman physics. So the maximum height, this is of course no air. So you should check that, and make sure that you get the correct answer, and then the total time. Time of flight should be twice V0 sine theta over G. Okay? So if you're a professional programmer, you have test suites. So you basically have code that you just test your code against to make sure that it's giving you the right answers. So it's always good to test your code and make sure that you get some of the things correct that you expect it to do. Okay, any other, yes?
On the homework, it says to test several different time steps. I don't know if there's like a minimum 4 or 2 or how many or when, whatever number we want. Cause you want a table, I guess, of a summary table or something. I don't know how many.
Yeah, I mean, tell me, like, I want you to explore, the problem numerically, so I want you to do what you explore it to the extent that you are, able to, and just see what's happening and see what interesting things come out of changing the time step.
And document it, was it?
Yeah. Are you converging on an answer as you decrease the time step, that kind of thing? Yeah, I want you to be as creative as possible when you're doing this. So I don't want to give you too much direction here. That's the fun of numerical methods anyway, is just to play around and see what you get. Okay, so now the one thing that we didn't talk about yet for trajectories of things in the atmosphere is the fact that the atmosphere is not constant. The density of the atmosphere is not constant, and that plays a huge role in the trajectory of an object that's coming into the atmosphere, for example. So let's just go ahead and calculate what that is. So, density of the atmosphere. So we'll use a thermodynamic argument here as opposed to more of a mechanical, classical mechanics argument. So let's just write down the conservation of energy. So dE is equal to T ds minus P dV plus mu dN. Has everybody seen this before in their thermodynamics class?
Yep.
Not yet.
Okay, well, this is the entropy, T is the temperature, P is the pressure, V is the volume, N is the particle number, and mu is what's called the chemical potential. Okay, so it just expresses the conservation of energy. So let's write down what this equation tells us. So we'll end up with some Maxwell relation. So if we say dE by ds at constant V and N, this is T.
Sorry, one more thing. What is mu again?
Chemical potential.
Chemical potential.
So if we take this partial derivative dE by ds holding V and N constant, then we get T. And if we take the derivative dE by dV holding S and N constant, this is minus P. pressure, and then dE by dN, holding S V constant, is mu, the chemical potential. Okay, so what we want to do, we want somehow to relate the chemical potential to the pressure. So we can take these two equations, and I can take a mixed partial. So if I'm gonna take the mixed partial, that means I wanna take d mu by dV. So I can write d mu by dV is equal to minus dP by dN. Okay. And now, because this is a Maxwell relation. And let's do manipulate it the physics way we do it in physics, which is to say, I can just treat these things as fractions, and write dN by dV is minus dP by dV. So I'm just bringing this up here and this mu down there. Okay? Now we have a differential equation relating P and mu, but I need this relationship between N and V. So let's just go ahead and use we can use the equation of state, PV is equal to N KT. Okay, so we'll use this. Let's solve it for N, because I want to, so N is equal to PV over KT. And then I can take my derivative, so dN dV is equal to P over KT. Okay? So now I can just plug that in for the derivative here. So we'll have P over KT is equal to minus dP over d mu. All right, now we're almost done. Now we can actually integrate the thing. So if I can just bring my d mu here, and I can write this as KT dP minus dP over P. Bring the minus sign over here. So this is just the log. So this says that minus mu naught is equal to KT log P over P0. All right, and now we have a relationship between the chemical potential and the pressure. So P over P0 is equal to E to the minus mu minus mu0 over KT. All right, so this says that the pressure is exponential in the chemical potential. And the chemical potential it's a real physical potential. it's just the gravitational potential energy of a molecule, so if this is the mass of a molecule. Okay, so we have that, P is equal to P0. So that's the exponential behavior. And this says, of course, that as h gets large, mgh, then this term gets small, so the pressure goes to 0 exponentially.
What's H?
The height.
Oh, height.
So, this is the Earth, it's radius of the Earth, if h is the height here that you're that is how it scales with the height. Okay, so we can parameterize this equation. And you can parameterize it. We want the density, so we'll write it down as the density. So this will be 1 minus A times H over T0 to the alpha. Okay, so I want you to use this equation. Actually, this is a pretty accurate equation for the following constants. If A is 6.5 times 10 to the minus 3 kelvins per meter, alpha is equal to 2.5 for air, and T0, that's the sea level temperature in Kelvin.
What's the unit of alpha?
Alpha is dimensionless.
Oh, okay.
Okay, so I want you to use that when you're solving problems that involve a change in density. And so let's see what your intuition tells you about the velocity. So let's suppose that if this is the radius of the Earth, and let's say h is way up here, so this is way out, and this is one of those Red Bull jumper guys, and you fall into the atmosphere.
Baumgartner, I think it's his name.
Yeah, Felix Baumgartner.
Yeah.
What does the magnitude of the velocity look like as a function of time?
I mean, eventually he's going to hit terminal velocity, right?
Eventually.
So, okay.
I guess terminal velocity changes. Actually, doesn't it?
Okay, well, it's the magnitude. Okay, so I think it's going to start from 0. It's going to exponentially go up, or it's gonna go up to the square, and then it's gonna maybe it's gonna plateau or maybe dip and then plateau.
I think it's going to be more like it'll start off like increasing as the square, and then just like linearly.
Because my guess is that he will fall, at the rate of gravitational acceleration, and his terminal velocity will be higher until the point he reaches a low enough elevation that his terminal velocity would make him go up to like the normal terminal velocity at 10,000 feet or whatever.
I think the end's gonna be a linear decrease because like terminal velocity depends on like how dense the air is, right? So you should see like starting at 0 and then like increase as the square, and then like kind of have like this linear tail.
Okay, yeah, I don't remember. It was something, yeah, I mean, it's you increase, and then you have to decrease and then come down and then somehow level off, right?
Yeah, that's what I drew.
Anyway, it's fun to draw the picture and then calculate it
Yeah,
and see what it looks like.
I just guess that because like there's a software called Rocket Sim where you can like simulate like the rocket trajectories, and it always looks like the velocity kind of like linearly decreases as the parachute deploys. I'm guessing that like a human body is like a really bad parachute, right? So
Yeah. Well, I think the funny part is that dip there, that's re-entry. that's where I feel like a majority of the re-entry energy is gonna be.
Mm-hmm. Yeah, the slowing down and getting up there, I suppose. Okay. All right, well, let's talk about a method to find zeros of a function. This is, this is something you want to do frequently, and you'll always find a use for it because it just pops up so often. So this is switching gears a bit here. So in order to do this, you have to assume that you can calculate the function. And its derivative. Okay, so let's draw a picture and see how this works. Okay, so we want to find the zero of the function. And in your code, I mean, calculators do this, to find zeros of functions, except, they have more sophisticated stuff on top of it. But this method here that we're going to do is called Newton's method. And it's really simple. So the first thing you do if you're going to find a zero for a function, or you want to try to find a zero for a function, is you'll take a guess. And we can call this G0. Okay? So take a guess, G0. Okay, then you calculate the function. Okay, so you want to calculate f and f prime at the guess. So what is f? Well, this is f at G0. It's that point on the graph. And it's also this distance here. Okay, and then we've also calculated f prime of x, so we know the slope at this position. And basically what you do is you just follow the slope to the axis, okay? And this is G1. Okay, so you have, there's a distance d here that's between them. So we have that G0 minus G1 is equal to d. But we also know that the slope f prime at G0 is the rise over the run, but that rise is f of G0. And the run is just d. So I can just solve for d. So d will just be f at G0 over f prime at G0. And then we can plug that in here, and we'll get G0 minus G1 is equal to f of G0 over f prime of G0, and then just solve for G1. So we get G1 is equal to G minus G0 f of G0 over f prime of G0. Okay, so then this you just iterate. And Gn plus 1 is Gn minus f Gn over f prime at Gn. Okay? So that's the Newton algorithm for calculating a function 0. And for well-behaved functions, it actually converges pretty quickly. But there are lots of pathological functions though where it doesn't converge, and so there are other methods that work better.
And if there's two, or if there's more than one root, it can be kind of like, it might take a while depending on if it's like right in between them. It might take a while to get to one of them. If there's two zeros.
No, I mean like functions like this where you have the function never actually crosses the 0. That'll freak out the Newton method. Yeah.
So we would essentially just iterate that until g to the n plus 1 equals
Till
g
some,
to the n.
yeah, I mean it'll converge, so
Yeah, okay.
you'll have smaller and smaller differences.
Yeah, I used to use Newton's method to cheat on my calc test in high school.
Really?
We had to find the value of a derivative. And instead of actually calculating it, I would just do use Newton's method and then use the answer button on my calculator to like replace one of the values I guessed, and then just hit enter over and over again until I got like either close to like an integer or like some multiple of pi, and go, yeah, that's probably the answer. And write that down.
Yeah, you do more work, but it's the one that you understand more.
It's actually it worked almost all the time.
Yeah.
Both were still.
All right, other questions over that? Okay, let's do another. Let's do an application of Newton's method that is actually very important. Okay, so let's do the following. All right, in computational physics, square roots are something of a thing that you really want to avoid. Especially if you're doing something that's, where you really have to have, it has to be fast. Square roots are, they're just notoriously slow. But the method, what we're gonna do here, which is basically just Newton's method to calculate the square root, is the fastest way that you can calculate a square root. It converges extremely quickly. So this is what all the chips use that in your computers, whatever, all of their floating point units. If you're going to calculate a square root, it's going to use this algorithm.
That's interesting because there's a method you can do by because there's a way of doing it by hand in decimal, but the way of doing it is binary is easier. It's interesting that actually calculating it is slower than using approximation and having it converge.
I've never seen the binary method.
Yeah, I used the decimal method before because I was a big nerd in high school and I didn't have a calculator. I'm like, I'm gonna just square roots by hand, and then I did it, and then I found out later that the binary method is like the decimal method but easier. It's really interesting.
You'll have to send me something. I've never seen that before. I mean, there was a discussion on some forums I was reading recently, and people had tried to come up with better ways to calculate the square root, but this was still the fastest.
Interesting.
Okay, so if we're going to calculate if we're going to use the Newton method to calculate the square root, then obviously we're going to be trying to find some crossing point. And so the way to do that is the following. So let's just first look at the square root function. So if this is x, the square root function, remember, just looks something like this. That's the square root of x. It goes to 0 at 0. It's got the little spike at the origin. And so if we want to calculate, let's just say I'm going to use x0 here. If I wanted to calculate the square root of x0, well, this square root of x0 is sitting up here. This is the square root of x0. It's at that point on the curve. So let's shift this function to the left. So that the square root of x0 is on the y-axis. Okay. So now I'm gonna draw this bigger. So now this function is now the square root of x0 plus c, where I'm gonna, let's see, I'm gonna calculate. This is the square root of c. I'm gonna say square root of c. Just x plus c. Okay, so the only thing that we have to do differently now is we're not going to be calculating it on the x-axis, we're going to be calculating it on the y-axis. So if my first guess then, remember when we were just doing the Newton method, my first guess was on the x-axis, but now since we've shifted it and we're trying to find this 0 here, my first guess is going to be on the y-axis. So let's put G0 here, and then follow this over to the curve. And then this, of course, will be, we're gonna follow that slope down to get G1. Okay. Yeah, sorry, I'm gonna call X0 then. So I don't know what, I just know my guess was G0 here, and that corresponds to some X0 there. Okay, so G0 was equal to the square root of X0 plus C. I'm just finding this is the curve, X plus C, so that G0 corresponded to this X0. And so we can write G0 squared is equal to X0 plus C. So I'm gonna need X0 here in a minute. This is G0 squared minus C. Okay, now the good thing about the square root function, so if f of x is equal to the square root of x plus c, then f prime of x is 1/2, 1 over the square root of x plus c. So this is just 1/2, 1 over f of x. Okay. So now, this is the distance 0 to x0. That's the distance over which we're going to follow the slope down. Okay, so we want f prime at x0 to get this slope. So f prime at x0 is 1 over 2 f at x0, but that's f at x0 is what we're calling g0. So this is 1 over 2 g0. Okay, so we want to get G1 here. So G1 is just going to be, G0 minus the slope that we follow for the distance x0. So it's minus x0 times that slope, which is 1 over 2 G0. Okay, so now we want to use this fact. We want to put everything in terms of G1 is G0 minus, and now we have G0 squared minus C over 2G0. And now we will just simplify this. So this is G1 is equal to G0 minus, let's see here, that's G0 over 2, and this will be plus C over 2G0, so this is half G, this is G over G0 over 2 plus C over 2G0. Yeah. G0 plus C over G0. Okay, so this is the that's G1, and then the simplest way to calculate it here is 1/2 Gn plus C over G. Okay, so let's see an example here. if, if, let's take C equals 2, and G0 equals 1. Okay, so we're trying to find the square root of 2, and we put in G0 equals 1. So let's just write down the iterations here, 0, 1, 2, 3, 4. And this is 1, so that's my initial guess. After my first iteration, I get 1.5. Then after my second iteration, I get 1.41666666. And then the third iteration is 1.4142156686, and then the fourth iteration, I've exhausted my calculators. These are, I think these are all correct up to the 2. So after 4 iterations, you get the square root. This algorithm doubles the number of significant figures at every iteration.
That's why it would be faster than, because the method I'm talking about is like digit by digit, so that would definitely be slower, I think.
All right, so you see the utility now of the Newton method to actually do something really quite useful. Okay, are there questions? All right, well, that's a good stopping point, so let's,
So I guess for the time steps, you don't really care, we just keep, how many we do as long as we find something interesting in the time steps that we do discuss in our paper?
yeah, I mean, explore it, you know.